Okay, so we're going to do a couple of shorter review. This is from something that you should all have seen in Calc 1. So go look at your calculus book, previous lecture, if you have still that material available to you. But I'm going to give you the short version of it, and especially focus on what we need. And in fact, therefore, actually, whatever I'm going to do in this particular video, this is part 1, there are going to be 3 of those, whatever I'm going to do is actually something that we're not going to use. So that's why I'm going to go rather quick over it, because it's not something that will be useful to us. It's not a way of calculating the integral, but it is a way to, it is important because I'm setting things up. Okay, so what's the issue? The problem is we have a function, give it like this, A, B, on a certain interval. So f is supposed to be a continuous function. I'm going to write this here, but now what does that mean, continuous? I'm not going to talk too much about that. What it means is we have, for us, what it comes down to is any function that we can dream of that is defined on this interval. So all the functions that we're going to deal with, if they're defined on an interval, they're continuous on the interval. It is important that we work on an interval. We will talk about what happens if you work on larger things, on the whole space or something like that, but for now on the interval. And what is the issue? Well, what we want to do is we want to fill this up here. Okay, we want to color this thing and then say this is the area underneath the curve, and we want to calculate that, given a certain function f. We know already certain things from pre-calculus and so on, right? From almost from kindergarten, we learned what's the triangle. Let's look at a simplest example of an area. Well, the second simplest. The simplest one I'm going to do in a sec. Let's look at this guy here. So here is one, and so we have this triangle here. So I'll color it green too, like this triangle. And what is the area of this triangle? Okay, so we have the formula, the area. What's the area of a triangle? Hopefully you all remember still this. I said this is something you learned in kindergarten or thereabouts. It is base times height divided by 2. Okay, what is it in this particular case? Well, I have put the points on my coordinate axis. You see that the base is 1 and the height is also 1. So 1 times 1 divided by 2, so a half. So that's one thing we know. There's actually one thing that's even easier. So I'm going to do this now too. Suppose we, let me make it, I don't have to put it in the coordinate system. Let me put it like this. Another thing that we know is a rectangle. So this is the area of a triangle here. Yeah. So here the area of a rectangle. So again, perhaps what I'm talking about is this green part here, right? So what's the area of a rectangle? That is length times width. Okay, so this is, depends a bit on what you call, this is the length, this is the width. Sometimes if you put it like this, you call the length height and so on. But it means the product of the 2 dimensions. Okay, these are the formulas that we learned. There are, more formulas. You know the formula for a circle and so on. Now, there are 2 issues here. First of all, what do we mean with area? Intuitively, we all know what we mean. But mathematically, it is mathematics. We have to express what does it mean for a number to be the area of a certain region. Okay, we're talking about regions, and we're going to find areas of these regions. And secondly, okay, we have some formulas, but clearly, if the function is something like this here, what's the area here? That is going to be, even if we define it, to actually calculate it might be pretty tricky. Okay, so we're going to actually answer both questions here. Well, I'm going to actually answer only one question. I'm going to say what is area, and then in the next videos we'll see how we calculate it. Okay, so I'll go back to my drawing. I have my function here again, something like this. I'm not making it too wild. And so what should we, if you try to explain to somebody what an area is, what would you say? I think I would say, well, you see here I painted it green, and it's the amount of paint that I used to paint it. That's the area, the amount of paint, right? I went a little bit outside the lines. I'm not very good coloring inside the lines, but okay, if I do it correctly, it should be the exact area. Well, this going out of the lines is actually something that we gonna do. And so what's the secret here? Well, what we're gonna do is we're gonna divide the interval in little pieces, all pieces of the same size. And so here is, let's call, a piece is gonna be a piece that goes from X to the next endpoint. So this, what I'm trying to do is this. Okay, so here is one little interval here. I'm going to call it the left point X, and I'm going to call the distance between the next point delta X, increment of X. Okay, now on that interval, I'm going to build a strip, a rectangle. And what do? At X, I go as high as the curve is. I stop there, and then so let's look at the other point. So what I would like to do is now go this part and look at the area of this strip. Okay, so let's first establish this. So if this green part is the area of the strip, then we can write down the formula, right? The area of the whole thing, of the area of the region, is going to be the sum. And remember, this is a Greek letter, capital letter sigma, S, for sum. And this means we're going to do the sum over all these areas of these strips. Right, so we divide the whole thing in strips, and we calculate the area of each strip, and we add them up. Okay, that's what the summation means. I can be a little bit clearer by saying, okay, I only want to work on this interval. Don't spend, this notation is really not so important. But what's the area of a strip? It's actually, I didn't make my life easier, right? Because it's still the same problem, okay? But now I'm going to do something drastic almost, but you see it actually will have, in the end, no effect. What I'm going to do is I'm going to flatten here. There's a curvature, right? The top is curved, that's the problem. I'm going to flatten it. Why do I do that? Well, because then what I have here is a nice rectangle, right? It's here. So we get this guy, and we know exactly what the area is. We wrote it down. So what I'm saying is the area of this strip is approximately. I'm going to say what I mean with that. But approximate is the area of this flattened strip. So when I write area of the strip, I mean the curved strip. Now the flattened strip, what is that? Well, that is length times width times length or height. Okay, what's the width? Delta x. What's the height? Well, okay, that's why we need a function, right? This point here, what is this point? Well, that is just f of x. The y-coordinate of that point is exactly f of x. So this height here is exactly f of x. So delta x of x. So I'm going to write my fx first. It's easier. Fx times delta x. But it's approximately. Why do I say approximately? Well, let's zoom in a little bit. What am I missing here? This is the original, and this is what I do. So this purple part here is what I calculate too much. Is it always the case I calculate too much? No. Let's look at a different example. Here, if I would, for instance, take a strip here. So, okay, so this is my x, my new x, and here is then delta x. So this would be the actual strip, the green one. I'll color it green again. Okay, but what is my purple, the flattened strip? What is that? Well, I flatten at this point. So what you see now is that the difference is between the purple and the green is this part here. Okay, and so now I calculated a little bit to the purple one is smaller, right? And in the previous one, the purple one is bigger, and so that's why I say approximately. Okay. But approximately is not good enough, right? We want equal. Now let's look here. I'm gonna make. Let's do. Let's see. I'll do it on this one. I'll do it one more time here. I'm gonna do a little bit exaggerated here. Let's make a big delta x here. So the purple one looks like now this, right? Remember, it's always the left endpoint that goes as high as the curve, and then we straighten from there out. Okay, so this is the axis. There is axis in this case, right? Now, how can I improve on this? Well, if you think about it, it's like painters, right? If you paint, your brush has a certain width. And if you're trying to paint something curved, but if your brush is too wide, you're gonna go over the curved line. So you're taking a smaller brush to get finer, to get better coloring, right? That's why I kept going out of my lines, because I put this on a very wide brush stroke. If I would do a much smaller brush stroke, then I would be much better to color in the lines. I'm not going to show you how I can color in the lines because I cannot. Okay, but let's just therefore look at strips of half the size. In other words, I'm going to go halfway. Of course, this means now instead of one strip, we're going to have two strips. Okay, what's the first strip? Well, the first strip is still basically the same, right? Well, up to there. And that's the second strip. No, sorry, it's my picture. I went to, let me undo this. I have to be a little bit. No, sorry. No, I was correct, sorry. So, so I'm going to halfway. So the first part is still the same, right? The second part is now slightly smaller because I have now gone down a little bit, and so my second strip is smaller. So what is my mistake? Well, this time this little blue part here is still wrong, and this little corner piece here, you could barely see it, is also wrong. But you see, that was part of the purple, but it is less the purple, because now the top part, the top purple part that is still visible is actually no longer counted. So by making, if I make delta x smaller, then the error, let's call that the error, right? The excess that you have, or sometimes it's sometimes excess, like here, or it is sometimes too little. You make the error smaller. That's the idea, right? The smaller the delta x, the less of an error I have, the less curvature and straight is invisible. Think of the Earth. We know that Earth is curved, right? We have all seen pictures of the Earth being a nice ball. I mean, there's still some people that say the Earth is flat, but that are crazy people, right? Okay, so the Earth is flat, is a ball. It's curved, very curved. Yet here we are standing on Earth, and you look at the horizon, and you see basically a straight line. It's straight, and at least the floors here, everything is straight. Why is that? Well, because we are so close up that the curvature for us is invisible. So the closer up, the smaller you look, the less curvature you see. That's this idea, because making delta x smaller makes the error smaller. And then this is the leap that calculus has made. And if you remember this from Calc 1, if you can make error smaller by making a certain quantity smaller, you can make the error gone by making that quantity 0. Now, you cannot just put the quantity equal to 0. You have to take the limit. So what does this now mean? Okay, so let me write up. Let's see first what we have. So we already said that let's write this formula here. The area of the strip is approximately. So instead of an equal sign that I had here, I'm going to write approximately. So this is still the same. And now I actually have a formula, fx delta x. Okay. By the way, this is called a Riemann sum. Well, no, sorry, this is not yet called a Riemann sum. I'll say in a sec what a Riemann sum is. Okay. But it is approximately, and the arrow becomes smaller, the smaller I mean delta x. So here is our official definition. The area of that region underneath the curve f. Under f is a function on the interval AB, okay? It's a whole long thing. We're going to get a nice abbreviation for that. Is what? Well, you take this sum here, you add up all these strips. Well, you actually flatten the strip so that you actually get this area. These are now rectangles, but that's not correct. There's an error, but the error gets smaller and smaller as I make delta x go to 0. So in the limit, the error is gone. So this is now my official definition of the area underneath the curve. Now this, I'm not going to keep writing this each time, right? So here's a nice formula for that. I'm going to write this as, this symbol here, an elongated s, is what we call an integral sign. Then we have the function f of x. We have the interval AB, and we're going to write this as endpoints. We call these the endpoints, A in the bottom, the left one, and B on top. And there's one little thing that I'm going to add, dx. You might question a little bit, why is that there? You'll see, it's naturally that it's there, and also it reminds me what a variable is. Very much so that if when I take the derivative, I also have this we have this notation, but this notation tells us not what the derivative is. The other notation, the so-called Leibniz notation, tells us what the variable is. Okay, and that's why we have this delta x, the dx here. Sorry. Now, okay, that's where we are. Okay, let me get rid of this. So now visually, what has happened? Well, when we take a limit here, this straight sigma here, we have now stretched out, and it has become this elongated integral sign. The a and b are now here, a and b, okay? And then we have the fx, and we take a limit, and that's what I mean to say. Instead of now a delta x, we get a dx. Okay, so visually you see that these two things are very similar, where we replace limit of a sum by this elongated integral sign. That's it. That's the definition of area. Now, for one thing, it should, if that's the definition, what about this guy here? It should give us the right answer, right? But the problem is that it is not easy to calculate the limit. Let me show you. I'm going to try to do this here. I'm going to divide this interval first in two parts. Okay, so my delta x here is going to be a half. So a half here, this is a half. So the first strip, they were purple, right? So let me make, my first strips are purple. I go all the way up, and then this one goes at the same height because I have to straighten this. Okay, so this is the error, the purple is the error I make. Okay, what's the area of this purple guy? The area, that's a rectangle, so I have to do, it's height times width. Height is 1, times width is a half. So the whole thing is a half. Okay. Now, what happens here? My picture is a little bit off. I'm very bad at drawing pictures. Yeah, let me do this a little bit better here, because I was not really in the middle here. The middle is somewhere here. Okay. Okay. So now, from this point onward, so this is a half, right? A half. From this one, we have, again, we make a straight rectangle like that. Oh, sorry, no, I meant to say. And again, we flatten this curve, right? We straighten this, and so again, we make an error here. Now, the error, we know that is eventually going to go away. Now, what is this? What's the area of this guy? Well, where is the first problem is already how high up are we here? Now, by symmetry, we know this is halfway also, so it's also at a half, right? So the height is now a half, and the width is still a half. So it's a half times a half, so 1/4. So we see that if I would write down this sum here, so this sum in our purple case would be a half, the first strip, plus 1/4, the second strip. That is 3/4. And what was it supposed to be? Oh, a half. Oh, that's not correct. But clearly it's not correct because I've made mistakes. So, okay, let's do it better and do, instead of 2 strips, I'm going to do 4. So divide each again in halfway. So this is the first one. The blue one is now still the same as the purple one. This is still my error. Now, the next blue one is going to be smaller than the purple one, so I'm going to have less of an error. Okay, I hope you can see what is going on, and this is the last one. Okay, so you see the errors are less, the blue is less than the purple. Now we have to calculate everything. Okay, so these intersection points are 1/4 and 3/4. I hope that's correct, right? So the width each is times 1/4, right? So here now delta x is 1/4. The previous current delta x was half. Okay, so the first strip, what's the area of this strip? Well, the height is now 1, right? This is 1, and the width is 1/4, so 1/4. What is this strip? How high does this strip come? I hope everybody sees this is 3/4, right? Okay, so this is 3/4 times 1/4, right? Because the width is still 1/4. This one is at position a half. Let me get rid of this guy here. This is still at a position and a half. So this is the height is a half, and the width is again 1/4. A half times 1/4. And then finally, again, symmetry tells me this is going to be at the height 1/4. So this has height 1/4, and width is still 1/4. So what is the blue sum now? I'll write it here. The sum is, so this is approximately the sum of the following things. So, okay, the sum, let me write down the sum. It's 1/4 plus 3/16 plus 1/8 plus 1/16. Well, we should put everything on common denominator to see kind of how big this is. So let's put everything on common denominator 14. So this will be 16, 4/16, right? And so this 3/16, this will be 2/16. So we get 4 plus 3 plus 2 plus 1, 10/16. Or 5/8. That's still not a half. It's supposed to be a half. But you see, you're getting closer to a half. It's better than 3/4, because 3/4 is actually 12. Here we had 3/4. If I put it on 16, that's 12/16, right? So 12/16, now we are better with 10/16. But we should have gotten 8/16 eventually. And if we keep doing this and take limit, you do get exactly a half. But, oh my God, this is a lot of work, and this is for something that is very straight. What have we all discovered? How am I ever going to calculate this? Exactly, you won't. So, couple more quick remarks before I go on how we actually will calculate this. So here we had, let's look at a function that is a little bit wilder, if you want. What happens here now? Well, let's look at a strip. If a strip is somewhere located here, let me do again, what is it, purple, right? So this strip would be here, and now I flatten it, and that, right? So what is the area of this strip? That would be, as always, fx, this is the function value, fx, times delta x. That's the width of the strip, right? Delta x. But f of x is a negative number. That doesn't sound correct. Area should not be negative. So, yes, this is the area with sign. So we allow that areas have a sign. So areas can be negative, which is kind of counterintuitive, but for mathematics, we will say that areas can be negative, because some of these values, f of x, can be negative numbers. So what is going on? If you think about it, if your strip lies located in this region, then it comes with a positive sign. If it's the same here, but if it's located underneath the x-axis, it comes with a negative sign. So what the integral really, so if we would calculate this a, b, fx dx, which we don't know how to do that, but I'm going to show you, then what we will find is actually that if we add this area and these two and subtract this guy from it, that's the number that this will give. You might say this is not satisfactory. Well, okay, yeah, but still, you can, if you want to calculate this really in a positive way, then just take absolute values, for instance, or something like that, okay? I'm not going to concern myself with it. Okay, so that's the first part. We have now defined what an area is. It is the limit of these sums, and this is what we call a Riemann sum. Riemann is, don't look up the name in the dictionary, it is, you have to look in the encyclopedia, because it's a mathematician from the 19th century who formulated this approach, although calculus is invented already much earlier by Newton and Leibniz and so on. They had already these techniques. Okay, that's the end of part 1.